Welcome back. Today, we're diving into one of the absolute coolest concepts in modern physics and space exploration. Seriously, we're breaking down a technology that honestly sounds a bit like magic. In this explainer, we're going to tackle the ultimate barrier to deep space travel. I'm talking about the fuel problem. And more importantly, we'll look at how we might actually solve it by harnessing light itself. Let's get into it.
So here's the core mystery we need to solve. How exactly do you fly through space without a single drop of fuel? I mean, it sounds straight out of science fiction, right? For the last century, our entire paradigm for space travel has basically been built on fire and exhaust. You burn stuff, it shoots out the back, you go forward. But the harsh reality is, our current rockets fall drastically short when we start dreaming about interstellar distances. We literally need a completely new way to move.
Section 1. The Space Travel Fuel Problem.
To really get why this is such a huge barrier, we have to look at how chemical rockets actually work. They store their energy in the propellants themselves. So to carry more payload, well, you need more fuel. But of course, fuel is heavy. It adds mass, which means you need even more fuel just to push the fuel you just added. It's this incredibly frustrating limiting cycle. To show you just how wildly inefficient this is for interstellar travel, check out this staggering number, 10 to the power of 53 kilograms. If you wanted to propel just a single microscopic proton to a tiny, tiny fraction of the speed of light, we're talking 0.002 c, you would literally need to convert the mass of the entire observable universe into chemical propellant. Yeah, the whole universe, for one proton. So clearly, fire and exhaust, they're fundamentally incapable of taking us to the stars.
So, we need a radical shift, a total rethink. On one side, we've got traditional chemical propulsion. This demands heavy, bulky, onboard fuel tanks, which drastically limits what you can actually bring with you and skyrockets the costs. But on the other side, we have propellantless propulsion. Instead of dragging all your energy with you in a massive tank, propellantless systems are clever. They harness the natural forces that are already out there in the cosmos, things like gravity, magnetic fields, and, yep, solar radiation.
Section 2. Enter the solar sail.
The solar sail is just such a remarkably elegant concept. Picture a massive, ultra-thin sheet deployed out in the vacuum of space, capturing the sun's electromagnetic flux to generate continuous, completely fuel-free acceleration. But to really grasp how this is physically possible, we kind of have to travel back in time a bit. Way before we ever launched rockets, the brilliant physicist James Clerk Maxwell theorized, all the way back in the 1860s, that electromagnetic waves carry both energy and linear momentum. Basically, he predicted that light exerts a physical pressure on any surface it touches. The math was literally sitting right there over a century ago, just waiting for our engineering to finally catch up.
Section 3. How light creates thrust.
Okay, so how exactly does a giant sheet of ultra-thin material turn completely massless photons into actual forward motion? Well, it all comes down to radiation pressure. Now, I know what you might be thinking. Wait a second, photons are particles of light, and light doesn't have any rest mass. So how on earth can something with zero mass push something else? It's a great question. Well, photons have absolutely no rest mass. They do carry kinetic momentum. Think of it like a billiard ball striking another billiard ball. When a photon strikes a surface, that momentum has to transfer. And that transfer, that creates pressure. That momentum transfer actually happens in a specific three-step process when solar radiation interacts with the sail. First up, we have specular and diffuse reflection. This is where photons hit the highly reflective sail and literally bounce off. This redirects their momentum and gives the sail a physical push opposite to the reflected direction. Second is absorption. Because, not all photons bounce. Some actually get absorbed by the sail material, and that deposits their momentum directly forward. And third, we have thermal re-emission. That absorbed energy, it heats up the sail. And as the sail re-radiates that heat away into space, it acts like a tiny secondary exhaust, giving the sail another microscopic push.
But let's get real for a second. How much push are we actually talking about here? Well, the math tells us that here in Earth's orbit, 1 square meter of a perfectly reflective sail achieves just a little over 9 micronewtons of force. And if that sounds incredibly small to you, yeah, it is. 9 micronewtons is roughly equivalent to the weight of a small ant just resting on the palm of your hand. That's it. That is the exact amount of pressure that sunlight is exerting on a square meter of space right now.
So you might look at that ant-sized push and think, okay, how in the world is that ever going to get us anywhere? But you have to consider this really crucial equation. Tiny force plus continuous time equals massive velocity. See, unlike a chemical rocket that burns hard for a few minutes and then just coasts, a solar sail never ever has to stop to refuel. As long as the sun is shining, it's pushing.
That tiny little push adds up continuously, second after second, month after month, and eventually, it generates incredible speeds that can easily surpass chemical rockets over long distances. It's the ultimate tortoise and hare situation.
Section 4. Real-world space sailing.
Moving from the theoretical blackboard to the actual launch pad, solar sails are really just one part of a wider family of environmental propulsion methods. Mission planners use these to trade hardware, mass, and time, all to save on precious fuel. We've got gravity assist, right, which basically steal orbital momentum from planets. There's aerobraking, which uses atmospheres to slow a craft down, electrodynamic tethers that generate drag using magnetic fields, and even magnetic sails that deflect the charged plasma of the solar wind. But among all of these options, the solar sail really stands out. Why? Because of its ability to provide continuous outward acceleration without having to rely on lucky planetary alignments or local magnetic fields.
And the coolest part, we've already proven that flight by light actually works in the real world. Back in 2010, Japan's IKAROS became the very first interplanetary solar sail, proving beyond a doubt that we could accelerate and control a trajectory using nothing but solar radiation. Then, in 2022, the Planetary Society's LightSail 2 successfully altered its orbit around Earth using just the sun's rays. And right now, NASA's ACS-3 project is actively testing advanced composite booms to build even larger, much more resilient sails. Guys, we are already sailing the cosmic ocean. It's happening right now.
Section 5. Beam-driven interstellar travel.
Now, if we actually want to leave our solar system, solar sails do face one major limitation. The inverse square law dictates that light intensity drops drastically the further you move away from the source. By the time a spacecraft reaches, say, the orbit of Pluto, the sun's light is a tiny fraction of a percent as bright as it is near Earth. The acceleration practically vanishes. But to overcome this, scientists are proposing something wild, replacing that fading sunlight with synthetic photons. Instead of relying on our sun, we'd point highly focused, incredibly powerful lasers from Earth, or maybe from orbit, directly at a deployable membrane. This lets us maintain immense targeted radiation pressure over incredibly vast interstellar distances.
Of course, to push a starship to neighboring star systems, we can't exactly just use a laser pointer, right? This concept demands huge, interconnected arrays of beam-steerable lasers with combined outputs of roughly 100 gigawatts. To put that completely massive number into perspective for a second, 100 gigawatts is enough energy to power millions of homes, and we'd be focusing all of that energy onto one thin sheet of material out in the vacuum of space. As you can imagine, the infrastructure and engineering challenge here is just staggering. But the payoff? The payoff is making the impossible possible. Using these gigawatt lasers, the ultimate theoretical goal, like the one proposed by the Breakthrough Starshot concept, is to accelerate tiny, lightweight nanoprobes to a massive fraction of light speed, specifically 0.2 c. That's 20% the speed of light. At that speed, sure, relativistic physics definitely starts coming into play, but it means we could actually reach Alpha Centauri, our nearest star system, within a single human lifetime. We're talking 20 to 30 years. Compared to the tens of millennia a chemical rocket would take, that is a real game changer.
I want to leave you with one final, pretty provocative thought from the research today. If you accelerate a laser sail to 20% the speed of light, it takes years to get up to that speed, but it also means you have absolutely zero onboard brakes. To slow down, you'd either need another massive laser array already built at the destination, or you'd have to rely on some incredibly complex braking maneuvers using the target star's own light. If your navigation is off by even a tiny fraction of a degree and you fail to be captured in orbit, your spacecraft is just going to keep going, carried entirely by its own immense momentum, sailing silently through the dark of space forever. So, knowing the incredible speeds involved and the absolute lack of brakes, are you ready to cast off? Thanks for joining me on this explainer, and keep exploring.